In this section 6.3, we're going to study inverse functions and relations. The objectives of this section is to find the inverse of a function and to verify whether two functions or relations are inverse of each other. Let's begin answering this question. What is a relation? And a relation is any set of ordered pairs, any. And the inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. The domain of the relation becomes the range of its inverse, and the range of the relation becomes the domain of its inverse. So in here we have a formal definition for inverse relation. Two relations are inverse relations if and only if, whenever one relation contains the element AB, the other relation contains the element BA. Let's begin with an example. Given the relation defined by the ordered pairs -2, 4, -1, 2, 0, 0, 1, -2, and 2, -4, let's begin by making the graph of this set of ordered pairs on a coordinate plane. So everybody knows how to graph points on a coordinate plane, and once we plot the points, the graph is going to look like this. We have the graph of these 1, 2, 3, 4, 5 ordered pairs on a coordinate plane, and this is the way that it looks. Now in B, let's find the inverse of this relation. How are we going to find the inverse of this relation? What we're going to do is, with each ordered pair, we're going to switch the order. The x becomes the y, the x coordinate becomes the y coordinate, and the y coordinate becomes the x. So, keeping this in mind, we're going to find the inverse of each ordered pair. So we're going to have 5 inverses. And the inverse relation, it would be the following: 4, -2, 2, -1, 0, 0, -2, 1, and -4, 2. And now let's graph the inverse relation. As we did before, we need to graph these ordered pairs on a coordinate plane, and this is the way that the graph of these ordered pairs look like. And the graph of an inverse relation is the reflection of the graph of the original relation over the line y equals x. So in here we have an image so that we can see exactly what is the meaning of this. In blue, we have the line as a dashed line. We have the line, this is the line that is called y equals x, and it is called more precisely the line of reflection. And in here, every point is reflected across this line. So the original function is defined in blue, and the reflection of this, or the inverse of this relation, is represented by the points in red. And as you can see, every point, this point in blue, is reflected across the line y equals x, and we get this point. This point also is reflected across the line, and we get this point in red. This point that is part of the original is also reflected across the line y equals x, and this point also reflected over the line y equals x. We can think also of this relation in the other way. Every point on the inverse is also reflected, so every point is reflected across the line y equals x. Is a relation a function? This is something that we need to have clear since the beginning. And the answer is not necessarily. And let's see what happens here. Remember that a relation is any set of ordered pairs, any. And here we have an example. This is another pair. This is a set of ordered pairs: 2, 3, 2, 4, 3, 5. It doesn't matter how we list the ordered pairs. The x coordinates doesn't matter that it's repeated. The y coordinates can be repeated. It doesn't matter. It can be any relation, any set of ordered pairs. Also, we can define a relation like with a diagram. In this diagram, the one at the left are the x values of the input, the y values are the output. And notice that in this, 4 is paired with 7, so we can say that we have the ordered pair 4, 7. 5 is paired with 2, and so we can say that we have the ordered pair 5, 2. Also, 5 is paired with the number 9, so we have the ordered pair 5, 9. And the number 8 in the input is paired with the number 5 in the output, so we have the order pair 8, 5. So you can see it's a relation is a set, any set of order pairs. On the other side, a function can be defined as a set of order pairs, as a relation, but there is a condition. The x-coordinate cannot be repeated. So in here we have an example. This is a relation, and what we need to do is to see if this relation is a function. Remember, if it is a function, the x-coordinate never repeats. So I have the order pairs 1, 2, 4, and 5, 25. As you can notice, the x-coordinates, the input, are 1, 2, and 5, and they are not repeated. So this set of order pairs defines a function. Also, you can think of a function in this way. For each input x value, there is exactly one output. Exactly one output. So here we have a diagram that we used in the relation at the beginning. And notice that in this case, for every input, there is exactly one output. For the input 2, the output is 4. For the input 3, the output is 8. For the input 4, the output is 8. And for the input 5, the output is 5. For each input, the input values are 2, 3, 4, 5. Each input has exactly one output. Notice that the output 8 has two different inputs. 3, the input, the output 8, and the input 4 and the output 8. But that doesn't matter. The output can be for more than one input. But for each input, it should be exactly one output. And this is something that we should always keep in mind. Every function is a relation, but not every relation is going to be a function. Think a little bit about this, and it's going to make sense to you. I repeat it. Every function is a relation, but not every relation is a function. And let's see what it would be, the notation for inverse. And let's read what it says over here. The notation f negative 1 represents the inverse function of f. The negative 1 is not an exponent. The notation f negative 1 doesn't mean 1 over f. F negative 1 is different from 1 over f. Let me explain that this f to negative 1 is not read like f to the negative 1 or f negative 1 like I did at the beginning. This, when you see this notation, is in this context that we're seeing inverse functions or inverse relations. It is read f inverse. So let me read again what I just read at the beginning. The notation f inverse represents the inverse function of f. The negative 1 is not an exponent. The notation f inverse doesn't mean 1 over f. F inverse is different from 1 over f. So let's make an example. Let's find the inverse of a function. Given the equation of the function, we're going to find the inverse of the function. So the function that we need to find the inverse is f of x equals 2x minus 4. So let's find the inverse of this. And in the first step, what we're going to do is to replace f of x for y. So we're going to replace f of x with y. And if we do that, f of x becomes y, and the equation is y equals 2x minus 4. Step 2, we're going to make a switch. Remember that when we define the inverse of another pair, what we did to find the inverse of another pair was to switch x and y. So it's exactly the same that we're going to do in here. We're going to switch the x and the y values, or the expression of the x and the y variables in the equation y equals 2x minus 4. So once we do that, the equation becomes x equals to y minus 4. And in step 3, what we're going to do is to solve this equation for y. So if we solve for y, this equation becomes x plus 4 equals 2y. We need to leave alone the y. We divide both sides by 2, and x plus 4 divided by 2 equals y. And if we simplify the left side, dividing each of the terms, x and 4 by 2, this becomes 1/2 x plus 4 divided by 2 is 2 equals y. And the last step, that is the one that it makes sense to the inverse, we're going to replace this y that we found, this y at the right in the previous equation that we have, we're going to replace the y for f of x, for f inverse of x. So we're going to replace the y with f inverse of x. And the solution that we have finally, the f inverse of x, the inverse of the function f of x equals 2x minus 4 is 1/2 x plus 2. Let's make a new example where we're going to find one more time the inverse of a function. And this time we're going to find the inverse of the function f of x equals x cubed plus 4. We already saw the steps, so we're going to follow exactly the same steps. We're going to replace f of x for y, so y equals x cubed plus 4. The next step that we're going to follow is to switch x and y, so the new equation that we have is x equals y cubed plus 4. And the next step, it will be to solve for y. So to start solving for y, we need to get rid of the positive 4. It passes to the left side subtracting, so x minus 4 equals y cubed. And finally, to get rid of the y cubed, or to undo the power 3, the exponent 3, what we need to do is to take the cubic root. So cubic roots, and the cubic root can be, the power 3 can be undone by using the cubic root. So what we're going to do here is to take the cubic root of both sides. So I proceed taking the cubic root of x minus 4 and also the cubic root of y to the third power. So we cancel the cubic root with the y cubed, and what remains at the right is y. So the radical and the exponent disappeared, and the cubic root in the left side is left. The cubic root of x minus 4 equals y. And finally, the composition, or I mean the inverse function of f of x, it would be equals. Remember that we need to do, the last step is to replace the y for the inverse notation. The inverse function, f inverse of x, equals the cubic root of x minus 4. And here we have, if you have a software, you have grapes, or you want to do it in Desmos online, you can find this application, graphic application. We have in here the graph of x cubed plus 4. And also, we have the graph of the inverse. The graph of the inverse, that is cubic root of x minus 4. And if we put both of them together on the same coordinate plane, we notice exactly what we explained in the example 1. The line in red in here, that is a dashed line, is the line y equals x. And if you notice in this graph, the black curve, that is f of x equals q plus 4, is reflected across the line y equals x, and the reflection of this graph is the one in blue, the inverse function f of x equals cubic root of x minus 4. Also, you can say that the inverse function cubic root of x minus 4 is reflected across the line y equals x, and the reflection of this is f of x equals x cubed plus 4. Both graphs are reflected, as we mentioned before, across the line y equals x, and this is what we call the line of reflection. Let's make one more example of finding the inverse of a function. And in this case, we're going to find the inverse of g of x equals 3 over x minus 1. Same as before, we switched g of x for y, so we said y equals 3 over x minus 1. The next step, it will be to switch x and y, so my new equation becomes x equals 3 over y minus 1. Let's leave alone the expression with the y, 3 over y, so the minus 1 passes to the left, adding x plus 1 equals 3 over y, and we notice that we have the y in the denominator. We don't need the variable y in the denominator, so we multiply across, and it becomes y times x plus 1 equals 3. So let's leave alone the y that is being multiplied by x plus 1. In this expression, x plus 1 passes to the right, dividing, so y equals 3 over x plus 1. And we only need to take one more step. And the step that we're going to take is to change the y for the inverse notation. So it would be, since the function is called g of x, finally the answer would be the g inverse of x equals 3 over x plus 1. And once again, here we have the graph of g of x, that is 3 over x minus 1 function, the original function. Here we have also the graph of the inverse, that is 3 over x plus 1. And together in the same graph, we have both of them. And if you study this, if you analyze what is done, both graphs are reflected across the line y equals x. Remember that y equals x is the line of reflection. We can also use the idea of composition of functions to verify inverses. You can determine whether two functions are inverses by finding both of their compositions. If both compositions are equal to the identity function I of x equals to x, then the functions are inverse functions. Let's see what does this mean. Two functions f and g are inverse functions if and only if both of their compositions are the identity functions. If we put this into symbols, what is being stated is the following. If we have two functions f of x and g of x, and these are inverse functions of each other, this is going to happen if the composition of f with g of x equals x, and the composition of g with f is also equals x. So we're going to make some examples to make this clear. In this example, we're going to verify if the functions that we have in here are inverse functions. So we're going to verify if f of x equals 5x minus 3 and g of x equals x plus 3 over 5 are inverse functions. And what we're going to do in here is to use the idea of compositions. First of all, we're going to find f composed with g of x. And what we're expecting in here is that when we find f composed with g of x, the answer is going to be x. So let's see. Let's begin with this. By definition, f composed with g of x is the same as f of g of x. That means that we're going to, by using the idea of the composition, we're going to replace f of g of x. We're going to replace the innermost function g of x into f. So g of x is like actually the input of f. So the function f is f of x equals 5x minus 3. So I leave the spaces to replace in the function f, and the input is not going to be x. In this case, my input is the g of x function, that is x plus 3 over 5, and I replace it on both sides. F of x plus 3 over 5 equals 5 of x plus 3 over 5 minus 3. Now, the left side is just notation. What I need to do is to simplify the right side. And I notice that I have 5 times x plus 3 divided by 5. So I'm going to cancel these 5s. And what I have now, it is x plus 3 minus 3. 3 minus 3 is 0. So this composition, it will be equals x. So f composed with g is equals x. Now let's see the other way around. What would be the composition of g with f? So by definition, g composed with f of x is the same as g of f of x. So in here, we're going to replace f into the function g. And the function f is 5x minus 3. So we're going to find g of 5x minus 3. And the function g of x is x plus 3 over 5. So we're going to replace in this function the x by 5x minus 3. So we have in here the space for the function f of x, that is going to be now the value dx, and we replace it into the right side of g of x function, and this becomes 5x minus 3 plus 3 over 5. Now here we're going to simplify in the numerator. Negative 3 with 3, negative 3 plus 3 is 0, it cancels, and what is left is 5x over 5, and 5x over 5 can be cancelled, and the answer will be x. So since both composition f composed with g equals x and g composed with f of x give us x, f and g are inverses. Let's make another example to verify if we have functions that are inverse. If these functions that we have in here given are inverse of each other. So let's verify if f of x equals x to the 5th power plus 2 over 7 and g of x equals to the 5th root of 7x minus 2 are inverse functions. And as we did it before, let's begin finding f composed with g of x. So we're expecting that if this is going to work out, f composed with g of x will be equals x. But it won't be enough. We need to find, after the finding of f composed with g, if the answer is x, we will have to find g composed with f. And let's see, by definition, f composed with g is the same as f of g of x. So again, my input into the function f is going to be the function g of x. that is defined as the fifth root of 7x minus 2. So this is going to be the value dx in the function f. So in here we're going to replace, I have f of x equals x to the fifth power plus 2 over 7. In this parenthesis, I'm going to input the g of x function, that is the fifth root of 7x minus 2. I replace it on both sides. And now what I need to do is to simplify the right side of this equation. And notice that I have the fifth root of 7x minus 2 to the fifth power. You can undo or you can cancel the fifth root with the power 5. And this becomes only the expression inside of the parentheses. That's what is left. And it will be 7x minus 2 plus 2 over 7. Now, to continue simplifying this, let me simplify the numerator. I notice that I have negative 2 plus 2 that are opposite. They're cancelled. And it's left 7x over 7. And 7x over 7, the 7 cancel, 7's cancel, and the answer is x. Therefore, f composed with g of x equals x. So it worked. The first part, it works. And let's see what happens with g composed with f of x. So g composed with f of x is the same as g of f of x. Now my input becomes the function f, and I'm going to replace the function f into g. Remember that g, the function f is x to the fifth power plus 2 over 7, and I'm going to replace it into the function g. So this becomes g of x to the fifth power plus 2 over 7. And replacing this on the right side of the function g becomes equals. Remember, I'm going to replace dx in the function g of x equals fifth root of 7x minus 2 by the f of x function, that is x to the fifth power plus 2 over 7. So this becomes equals the fifth root of 7 instead of the x. I'm going to copy the function f of x, and the function f of x, the right side of the function f of x is x to the fifth power plus 2 over 7 minus 2. Now, how do I simplify this expression? I have a 7 that is inside of the radical. I have a 7 multiplying the expression x to the fifth power plus 2 and divided by 7. Let's cancel. That's what proceeds. 7 that is multiplying with the 7 that is dividing. And now what I have is the equation that says the fifth roots of x to the fifth power plus 2 minus 2. Let's simplify 2 minus 2. It becomes only the fifth root of x to the fifth power. And I can cancel the powers. The power 5 with the index 5, with the index of the root that we find in. And this becomes equals x. And once again, we have the value dx. Therefore, because the composition of f with g is x, and the composition of g with f is also x, f and g are inverses of each other. Not always is going to happen. Not all the functions that are going to be given to us, or in all the cases, are going to be inverse. And if it happens that after I simplify, if I start simplifying and one of these compositions lead us to something different from dx, we can stop the procedure. And just to mention, the functions that are given to be tested are not inverse functions. And here we have a new idea that is going to be only graphically, and this is called the horizontal line test. Every function has an inverse, but the inverse in not all the cases is going to be a function. There is a graphic test that can help us to determine if the inverse of a function is a function or just a relation. And this is what states this horizontal line test. If no horizontal line intersects the graph of a function f in more than once, then the inverse of f is itself a function. Let's make an example where we illustrate what we state in the horizontal line test. We're going to use the graph of each function to determine whether the inverse is a function. So let's begin with this example. This is the graph of a linear equation, and what we need to do here is to decide if this function has an inverse or not. So every time that we draw a horizontal line, it is supposed to intersect my graph in exactly one point. If you notice in here, when I drew this horizontal line is intersected in one point. Let me draw another one. Also, I notice that this graph intersects my linear function in one point, and you can continue doing this for as many times as you want. And every time that you draw a horizontal line, what is going to happen is that this horizontal line is going to intersect your graph in exactly one point, no more than once. So this function has an inverse. The inverse of this function is a function. Let's see a second example. In this second example, we have this quadratic function, and what we need to test again, it is if I cannot find a line that intersects my graph in more than one point. If I find at least one line that intersects the graph in more than one point, the graph of the inverse, it won't be not a function. And see what happens. Here I have this line that intersects this curve in 1 and 2 points. So because of this, because the graph is intersected by a horizontal line in more than one point, this graph, the graph of a quadratic function, has an inverse, but the inverse of this, it will be not a function. Let's see another example. This is the graph of the absolute value function. And again, think of a line, of a horizontal line, and graph it, and notice that when you do that, this graph intersects, this horizontal line intersects my graph in more than one point again. And the horizontal line test says that it has to intersect it in exactly, no more than once. So in here, since we have that the points of intersection between the graph of the absolute value in this case and the horizontal line is, we can see more than one point of intersection, it means that the graph has no inverse that is a function. So the inverse is not a function. And one more, we have the square root function. And again, if we draw a horizontal line, let's see what happens. I have one point of intersection when I do it. So every time, what I need to test is that every time that I do this, I have only one or more than one point. As you can see here, guys, as long as I keep on doing this, every time that I do it, what is going to happen, the line that I draw, the horizontal line that I draw, and the graph are getting intersected but in exactly one point. Therefore, the graph of the square root of the inverse of the square root function, it will be a function, because every time that I draw a horizontal line, the intersection is in exactly one point. So yes, this has an inverse. Let's see the next one. I have the same in here. I have a cubic function. Think of for a moment about the cubic function. If you keep on drawing a horizontal line, what is going to happen? It's going to be the graph intersected in exactly one point or more than one point. And what is going to happen is that the intersection between any horizontal line that you draw and the curve that represents the cubic function that is given here, you're going to notice that the intersection is only one point. Therefore, yes, this function has the inverse of this function will be a function. And the last one, the reciprocal. The reciprocal function, or the function that we have here, is y equals 1 over x. This function, we keep on drawing horizontal lines. Every time that I draw a horizontal line, it's going to happen that the intersection between the horizontal line and this curve is going to be, or this graph is going to be exactly one point. You can draw as many horizontal lines as you want, and then you do it, the point of intersection is going to be only one between the graph and the horizontal line. Therefore, the inverse of this function, the reciprocal function, it will be also a function. And here we have an application of inverse functions. The function given by f of x equals 5 over 9x plus 32 converts x degrees Celsius to an equivalent temperature in degrees Fahrenheit. So what we need to do in here is to find the inverse of this function. And what is going to happen in here, guys, is that when you see all the procedure that you know how to solve, how to follow it, you know what is the steps to find the inverse of a function, the equation that you're going to get is an equation that it would be called the Celsius formula, that is going to convert x degrees Fahrenheit into Celsius. So in here we have the steps that are going to show you, that is going to lead us to find the inverse of the function f of x that converts x degrees Celsius to Fahrenheit, and we're going to find the inverse, And once we have the inverse, what we're going to get is the Celsius formula that converts x degrees Fahrenheit into Celsius. I know that you have used these formulas in your science classes, and once we have proceeded with the steps that you know, the Celsius formula becomes the inverse function of x, that is equals 9/5 times x minus 32. And finally, I want to leave these exercises for you. We have an equation, we need to find an equation for the inverse function of x, given that f of x equals to 4x minus 5 over 2. So you have this set of exercises, and you know how to proceed to find the inverse. And one of these choices that you have in here is going to be the answer of this. So you can work on your own to find this answer. And here we have another exercise. Find an equation for the inverse of f of x, given that f of x equals x minus 3 to the third power.